Okay, good afternoon yet again. I've just done some general relativity and I just figured I'd do a little bit more, just to be different, because you get bored doing physics all the time. So this is going to be on chemistry, because somebody asked me a question this morning. They asked me about methane. What is it? It comes out of when you switch on your gas cooker, it comes out of it. So this talk is on organic chemistry. Now I'm not a chemist, so I may get some things wrong. I'm not a biologist. I'm just doing this for the sake of the chemistry of life, if you like. And it's elementary. But it's actually it can get complicated, get much more complicated than this. Now, if you're an 8th grader doing chemistry, you can understand this. If you're a 7th grader, you probably understand it. If you're a 5th grader and you don't know about chemistry, you will pick it up. And it's useful. Basically in chemistry there are two types of bonds. Well, there's probably lots, but I'm not a chemist. Covalent bonds involve sharing of electrons. And I could never understand this one quite well either. Ionic bonds are the other type, and they seem to share electrons too, but one way or another these are definitely sharing electrons. Ionic bonds happen between metals and non-metals. For example, the metal sodium and chlorine, NaCl, common salt. Now, covalent bonds involve only nonmetals. Okay, now let's see if I can remember all the nonmetals in the periodic table. Now I'm assuming you guys know the basic symbols. For example, well, I'm not going to go through them all. You'll see as it comes up. Well, some gases at room temperature are hydrogen, oxygen, and nitrogen. They don't exist as elemental. They exist as molecules like this. Okay? And the other gas is chlorine. Fluorine is a non-metal, I guess. Iodine, I don't know what acetine is, it may be, I don't know, I'm in between them. Sulfur, carbon, silicon, very interesting one. Star Trek had a program one time where they went to a planet and instead of having carbon as the basis for life, they had silicon. Very good idea. Because the valence of carbon is the same as the valence of silicon. Yeah? What's a silicon? A silicon is a convict who breaks out and he gets himself brought back in a hurry because he forgets to change his clothes. Anyway, never mind about that. And of course, all the noble gases, or the inert gases as I call them, in that whole column, they're all nonmetals too. So that's all the nonmetals we have. So when we're talking about covalent bonds, it only involves these guys. It doesn't involve chlorine. It doesn't involve zinc. It doesn't involve any of the rest. Because when you look at the periodic table of the elements, non-metals are all up there and the metals are all here. Except for H is up here. Okay? Alright, so that's where we're beginning. Now the basis of life comes from the fact that carbon is able to make very strong covalent bonds in all sorts of different ways. Yeah? Makes the DNA molecule, and I don't know, I'm not a chemist, but one way or another. Let's have a look at basic organic chemistry. So using our nonmetals, what can we do? Carbon makes strong covalent bonds, and we put carbon compounds together just like Lego. So we can make all sorts of structures. I wanted to start a company that could make new structures, not the life ones, totally new ones. Somebody is interested in that, get at me, because I've got some ideas, right? People are all the time making smaller and smaller devices. This is as small as you can get. You take the carbon atom and you make all the different things that you want to do with it. So, we're going to begin with carbon and hydrogen. Hydrogen has a proton in the middle, an electron on the outside, but at the first energy level, or the first shell, if you like, you want to call it a shell, in the ground state for hydrogen has a space. I represent the space by an X. I think chemists do this, and here's the electron. Now carbon has 6 electrons altogether. So 2. Oh, I didn't do that the right way, it doesn't matter. 2 go into the first energy level, the shell. There's nothing wrong with calling it a shell. 2 go in the K shell and 4 go in the L shell in carbon. Now the L shell, K shell can take 2. But the L shell is stable. Stable, it can take 8 electrons to make it stable, so that it doesn't need any more, then you have to go to the next shell. So let's see what carbon will look like in this notation. So we have 1 electron. Let's see if this is running. Yeah, it's running. And 1 vacancy in hydrogen, and 4 electrons and 4 vacancies in carbon. So therefore, what can we do? Let's start playing around with our Lego set. Okay, let's start sticking hydrogen atoms in here. Well, we can put a hydrogen atom here, 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 and here. Why? Because this electron can go in this slot, 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 this electron can go in this one, and these 2 as well. Now we don't want to keep writing these legs all the time, so we just write it like this. We write it like that. And that's the basis of just about everything. When you've seen that, you can do a lot. You can make anything you want. You can make any Lego set in your imagination once you know these basic structures. You know, you can make rings, you can make squares, you can make, let's see why, okay? All right, we're going to use the legs to represent the sharing of 2 electrons, a covalent bond. Now I'm sure chemists are going crazy looking at me, a physicist, talking about this stuff, but we can still manage. It's good enough for school kids maybe. Actually, it has to be the best for school kids, and it is the best. We'll manage, don't worry. Alright, so maybe chemists won't complain. Maybe they don't even do it this way. So one way or another, let's continue. So this here, let's do H2O. Oxygen is atomic number 8 and atomic weight 16. So it has 2 electrons in the K shell, has 6 in the 8, plus 2 vacancies. A valence of 2 would be like, we won't get into technology. There are spaces for 2 electrons in the oxygen atom. There's a space here, a space here, 2, 4, 6. So therefore we can come along with our hydrogen atom. And another one. Sorry. With 1 electron and 1 vacancy. And we can share here and here. Here and here. And the upside and down, and we can't do it. Let's see what this is. Well, that's what it is when we put in our leg notation. That's oxygen, hydrogen and hydrogen. Well, we have 2 hydrogens and 1 oxygen, H2O. We're going to give this guy a name. First of all, we'll give it a formula. C1H4. 1 carbon and 4 H's. But it's just CH4. It's actually methane gas. Yeah? Marsh gas, call it what you want. Okay, so that's our structure. That's how we're going. Let's continue and make other structures. And that's what nature does. Without this stuff, we wouldn't have life. It's a mini computer. Not really a computer, it's a bridge building thing. It's just about everything. Well, we'll start off with this structure. Well, we could come along and instead of adding just a H here, we could take a structure like this, stick them together. We can do that. Now look at this. 4. Twice the number of C's plus an extra 2. 6. Twice the number of C's plus an extra 2. For any n, we have H2n plus 2. But there's a structure that's possible, because all we're doing is we're taking all those 2 H's per C plus 2 on the end. Very simple. This is called ethane. Let's do one more. Now, 3 and 3 and 6, add 2. go. Methane, ethane. This is called propane. We can keep going. One, two, three, four, five, six. I'm just guessing at this one. And these are called the alkanes. And they go from gas to liquid to solid. Butane gas, propane gas, ethane, methane gas, then liquids, octane, septane, nonane. We can cook with these guys. Gasoline is what we put in the car. Jet engines take really low quality alkanes. Then we can get right up into the solid. And they make candles. Okay? So, this is the structure. Let's just investigate octane before we change this pattern. How many carbons in octane? 8. How many H's in octane? Twice 8 plus 2. 16 plus 2 is 18. Count them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 6, 8 and 8 is 16, 17, 18. Octane. Let's complicate the pattern a little more. We'll take the same structures. Oh, I shouldn't have erased that. I could have kept it. Wait a minute. Now, a minute ago I had water. Let's take one of these H's away. And I'm left with this as a proof. So I'm going to stick this structure onto here. It's Lego. Remember I said that? Actually, I'm not even going to bother doing that. I'll just write it because it occurs so often. NaOH, sodium plus this hydroxyl radical, that's sodium hydroxide. It's drain cleaner. Sorry. I get this structure. And this formula, structural formula, molecular formula, CH3OH. Now, if you heat wood without burning it, you can get this stuff. It evaporates off it. It's called methyl alcohol from distilled wood. Okay? Methyl alcohol, methane, we name it methyl alcohol. Let's do the next one. Actually, I'll clean this. I'm going to leave the names. If you scroll back, you'll see I had this compound. That was ethane. Yeah? What's it going to become if I add OH instead of H? Ethyl alcohol is the one that humans like. It's found in beer, wine, and whiskey. Ethyl alcohol, this is poisonous, yeah, but not as poisonous as this one. This one will kill you. But this one, you can, humans learned how to do it. Actually, civilization grew up on the capacity on humans discovering the ability or the mechanism to make beer. Yeah, they sowed corn, whatever it was, and they learned how to ferment it to make bread and beer. And that was between the Tigris and Euphrates River in what is now Iraq. Okay, the heart of civilization. I don't know, maybe 12,000 years ago. I don't know if they have it all figured out yet. But yeah, when you can make a little bit of beer and bread, you're doing fine. People would settle to do this. What else can I say about this? Let's do octane. Octane, we'll do it. Now, clearly we can have methyl alcohol, ethyl alcohol, propyl alcohol. You've seen this one. You see it on rubbing alcohol, butyl alcohol, heptyl alcohol, hexyl, and so on, and octyl alcohol. So octane becomes octyl alcohol. Now let's count the H's. 8 and 8 is 16 and 1 17. And an OH. Octyl alcohol. Let's try another trick. Now, COOH, we can have two legs of the C. 1, 2, oh gosh, wait a minute, that's not right. COOH. Now, carbon has 4 legs, so let's check that. I have to come back to that in a minute. Chemists would know this. One way or another, we can take this structure. I'll come back to this, I'll figure that at the next time. I'm not a chemist, and I haven't looked at this for donkey's years, 30. So, CH3OH is an alcohol. But if I replace it with COOH, I get methanoic acid. if I do the next one, let's do this. I get ethanoic acid, C, and so on and so forth, yeah? Now I think ethanoic acid is vinegar, but I'm not sure. Ethanoic acid would be vinegar, because you can make vinegar using wine. Wine, you let it ferment, and it becomes vinegar. Okay, so I guess that's right. Ethanoic acid is vinegar. Vine agar, sour wine. I know they have an E in here, but I call it AGER. I do things peculiarly. Okay. We'll just do, so I'm coming in a minute for dinner. Do one more thing. Oh yeah, this is octanoic acid. Let's count the H's and the C's. 8 negative 16 and 117. And that's what it looks like. Okay? We'll do something just for this class. I'll come back to more of these ways of arranging things, but I just want to do something interesting. NH3 is ammonia gas, right? If I take away one of the H's, I'll leave a leg. In other words, a place for hooking onto one of these legs. So, ammonia sounds like something we're familiar with. That's an acid. That makes the thing an acid. And this sounds like ammonia. What is that going to be sound like? Ammonia acid? No. Amino acid. Like I said, I'm not a chemist, I haven't looked, but I think this is called glycine. I'm not sure. But it's the simplest amino acid. Strangely enough, if you look at the spectra of the Magellanic Clouds and you look at the light that comes from those clouds in outer space, you get hydrogen, carbon, and a lot of other things. But you also get, in outer space, in deep space, you see there's lots of amino acids. Strange. The basis of life is out there in outer space. Okay, that's enough of this part. I'll do more organic chemistry just because it's fun. I should really probably look up stuff because I don't really, I know a little bit about it, but not that much. You know, an organic chemist would do a better job. I just want to show you the way things get made up. All the structures of life work like this. I'd like to work up to getting a map of our DNA, just to show you how the DNA molecules work. But I forget. I mean, actually, I never even looked at it, so I never learned it. But I can figure it out for next time. One of the times. That's this talk.